Welcome to lesson 6.2, using models to solve equations. In this lesson, we are going to solve equations using a method called balancing scales, both to model and to verify the solution when you're solving equations in algebra. So sometimes systematic trial and inspection, which you learned in the last lesson, they're not necessarily the best way to solve an equation. Or if you were looking for another way to show your learning, particularly using pictures and symbols, this would be another great strategy to use. So down here I have shown an example of what a balanced scale might look like. So we have the scale down here, and then we have the two sides of the scale, which we're going to call pans. So basically, when the pans are balanced, meaning when this side of the scale equals that side of the scale, it is balanced, right? They both equal the same side. So in this example, we have 20 grams over here. And then on this side, we have 10, 5, and 5. So if I was to add those three numbers up, that would equal 22. So example number 1 represents a balanced scale. But if I wanted to write an equation to represent this balanced scale, what would that look like? Because this does represent some sort of an equation. So this would represent 20, because that's the number we see on this side of the scale. 20 is equal to 10 added to 5 added to 5. So this is not necessarily an example of how you would use this to solve an equation, because we weren't solving for anything in example 1. It's just getting us used to what the idea of a balanced scale is and what it represents and how it can help us when we go to solve an equation, because we know an equation is exactly like a scale in real life. Just like a scale in real life, it's balanced when both sides weigh the same thing. In algebra, when you're solving an equation, all you're doing is trying to balance both sides of the equation so that they're equal. Next, we're going to look at two examples of a balanced scale and how you would represent this as an equation when you have an unknown mass in one side of the pan. So let's look at example number 2. So if I wanted you to express this as an equation, I see a question mark, so I don't know what the mass of that red box represents. I see 3, I see 5, and then on this side I see 7 and 10. So if I was to represent this as an equation, I would use that red question mark box as my unknown. So that's my x, or my variable, because I don't know what it is. So x added to 3 added to 5 equals 7 added to 10. Because we know that both sides of the scale have to be balanced. Let's just condense this a little bit, because there are some numbers that we can add together. So I still don't know what my x is, but I know that 3 added to 5 is 8, so I can make that x plus 8 is equal to, and then if I was to add up my 7 and 10, I know that's 17. So this scale represents the equation x plus 8 equals 17, or a number plus 8 equals 17. And now we're in more of a position to figure out what that red question mark box equals to, so that our scale is balanced. And we're going to look at example 3 and follow just the similar process that we did and represent this scale as an equation. So I'm going to look at the left side of the scale, and I see that's 8 grams plus 11 is equal to, I'll use n for the red question mark because I don't know the value of that box, added to 4. So this is what this balanced scale represents, but we can condense this equation a little bit more clearly, because I can add my 8 and 11. So 19 is equal to a number added to 4. So now, having created these equations, we're now in a position where we can take the next step, which you'll see on the next slide, in how we go about solving this using the balancing scales method. So here's an example that we're going to do together to show the steps in how you would show your work using the balancing scales method to solve an equation. And you'll have to excuse my drawing here. It's not quite so easy to draw on the iPad, but here's my balance scale. So I have my unknown mass, which is A, and then I have 7 grams on that side of the scale. And then on the other side of the scale, I have 25 grams. And in your head, you could probably just figure out what it is. But to show your work, we're just going to go through this example together. If you recall in Unit 1, when we were learning how to solve algebraic equations using algebra tiles, the rule was you want to try to get the variable by itself. You want to solve for A, so A equals what? And in order to do that, you need to remove whatever else is on that side of the equation. And what you do to one side of the equation, you always do to the other side of the equation. So that the same kind of principle, the same rule applies here. So I see that there's only one A, and there's 1 7, and then on this side of the equation we have 25. So if I was to represent this as an equation, it would be A plus 7 equals 25. Using the balancing scales, I know I need to get rid of this 7 from this side of the equation. But if I get rid of 7 from this side of the equation, what do I have to do to this side? I need to get rid of 7 as well. So in order to show that using your balancing scales, I'll just draw another scale here really quickly. So I have 2 boxes still on this side. However, this time, I'm going to break that 25 into 7 and 18. When I add 7 and 18, it still equals 25, so it still equals and represents the same thing. I just know that because I need to get rid of 7 from this side, I'm going to need to get rid of 7 from the other side of the equation. So just to make my work a little more clear, I've just split the 25 into 18 and 7. So what do I need to do now? So I need to get my A by itself from this positive 7. So how do I get rid of positive 7? I subtract 7. So I'm going to take my 7 and I'm going to subtract 7. And what you do to one side of the equation, you do to the other side of the equation. So I need to subtract 7 from that side of the equation. And so what does my new balance scale represent? I'll just draw another one out here. So now that I've gotten rid of both of the 7s from both sides of the balance scale, I am now left with A equals 18. So in this example, that unknown mass, the A, equals 18. However, the next step to fully show your work would be to take that 18, put it back into your balance scales, or put it back into your equation, and just to verify your solution, to make sure that you didn't make a slight mistake, and to make sure that it is true. So both sides of your equation are now equal. So I just wanted to do one more example, but an example that includes more than one variable. So in this question, we have 2 variables on this side of our equation. We have a 6 and we have 28. So as a written equation, this would represent 2w, because I have 2 w's, added to 6 equals 28. So that's the equation that this balance scale would represent, but we're still going to solve it using the balancing scales method. And it's going to follow the same process as earlier in the previous example. So when I look at my equation, I see that I have 2 w's, a 6, and a 28. And I know I want to solve for what does w represent, because both of these w's will equal the same amount. They're both a w, they're not going to equal different values. They will have the same value, but I want to figure out what one w equals. So I need to get my variables by themselves, and I see here that there's a 6, and the 6 is kind of stopping us from getting those variables by themselves. So I know that I'm going to need to remove the 6 from the left-hand side of my balance scale. So I'm just going to draw it out here again. Sorry for using a different color. However, I'm going to split that 28 into 2 parts. Remember, I did that last time, so I still have w, w6, but I know I'm going to remove the 6 from both sides of the equation, so I'm going to split my 28 into 22 and 6, because 22 plus 6 still equals 28. It still equals the same thing. It just makes my life a little easier in showing my work. So my first step is I have positive 6 on this side, so I'm going to get rid of positive 6 from this side. What I do to one side of the equation, I have to do to the other side of the equation, so I'm going to get rid of my positive 6 from that side of the equation. I'm going to redraw out my balance scale just to see what I am now left with. So I now have 2 W's. I don't have my 6 because I've minused it from both sides of the equation. And then I have 22 left on this side of the equation. So we're not quite done at this point, because what this shows is that 2 W's equal 22. But I want to figure out what only 1 W equals. I don't want to know what both of them equals. I want to know what 1 equals. So in order to do that, I need to split my 22 into 2 equal parts. And I do that because I have 2 W's. If I can split my 22 into 2, I can then figure out what each of the individual W's represents, which, like I said, it will be the same value. So on this side, I have 2 W's. On this side of my balance scale, I need to split that mass into 2. So then, again, sorry for the different color, it becomes something that looks like this. So I still have my 2 W's. I haven't done anything with them. But if I split my 22 into 2 equal parts, what do I get? 22 divided by 2 is 11. So again, we haven't changed the weight or the side of that scale. We've just represented it in a different way. So now this becomes much more clear what 1 W represents. 1 W, let me just get my pointer, 1 W equals 11. This W equals 11. So in this example, W equals 11. Please review page 226, 227, and 228 in your textbook if you need this idea reinforced, or you need to go over a couple more examples, because it also does lay it out very clearly in the textbook.